this lesson, we will review Bayes' theorem. So far, we used probability to quantify certainty and uncertainty in classification. Next, we will study Bayes' theorem as it forms the foundation for the naive Bayes classifier. Probability has two sides: theoretical, which is defined by axioms and mathematical rules, and an applied side, which helps us interpret observations and make predictions. For instance, in classification, we use a probability to infer the most likely class based on training data. And this is the core idea in knowledge discovery. In Bayesian thinking, probabilities represent degrees of belief expressed as distributions of possible parameter values. The process follows three key steps. We start with an initial belief called the prior probability. Then we observe new data, the likelihood, and update our belief using the Bayes theorem, which is also called the posterior probability. One notable example is election forecasting. We notice how polls continuously adjust probabilities for different candidates. This is how Bayes' theorem looks like. The probability of a hypothesis being true given some evidence is equal to the probability of observing that evidence given the hypothesis multiplied by the prior probability of the hypothesis. The division by P of x serves as a scaling factor to ensure that the result stays between 0 and 1. So, in other words, P of h is the prior distribution probability, what we already know. The likelihood, P of x given h, probability computed based on the observed data. And what we're after here is calculating the posterior probability, which depends on both the prior and the likelihood. In summary, Bayes' theorem works by expressing prior belief through a probability, modeling data using likelihood, and updating our belief by combining the prior and the likelihood. Let's consider an example here. We typically assume that a fair coin has a prior probability of 0.5 for heads, 0.5 for tails. However, if we start to flip that coin and we start to observe that heads appears as 90% of the time, so our updated posterior probability will reflect this shift, and we'll start to adjust our belief that the probability of head actually is not 0.5, maybe more than that. Bayes' theorem can be applied to medical testing. To give context, in medicine, doctors often start with fast and inexpensive tests for screening, and if these tests turned out to be positive, then they go ahead and order the more expensive and the more elaborate ones. This is great, but the issue of false positive in these tests can skew the interpretation. So Bayes' theorem can be helpful here to compute what we call the positive predictive value, which is going to measure the accuracy of the positive that we got from the test. Let's walk through this example. Suppose that cancer is present in 1% of the population, which means 99% of the population do not have cancer. And for the test performance, 80% is true positive and 90.4% is true negative. False positives are 9.6 and false negatives is 20%. So this is really bad for a test to say it's negative, but it's positive, level of 20%. Our goal here is to compute the probability of cancer given a positive test, which can be articulated as the ratio between the true positive and the total of positives, which comes from the true positive and the false positive. Now we can use the data that we have to compute the needed probabilities, to plug them into Bayes' theorem, and we end up with 7.76% chance if a test says it's positive that one actually has cancer. If we want to think about this result, this is really a bad result. 7% is significant. And the reason we got this 7% is due to the false positive rate. The false positive rate is high, so it skewed the result. Let's take a look at another example. Suppose it's Sunday morning and we want to invite our friends for a picnic, but the sky is cloudy, so we are not sure whether it's going to rain or not. So we want to compute the probability of rain given a cloud. We start to gather more information. So 50% of rainy days start cloudy, which means the probability of cloud given rain is 0.5. Cloudy mornings are common, 40% for probability of cloud. And this is usually a dry month, so 3 out of 30 days tend to be rainy. The probability of rain is 0.1. We go ahead and plug in the values to Bayes' theorem, and we end up with a percentage of 12.5. So even though it's cloudy, the probability of rain is still low, which means more likely it's going to be a good day for the picnic. In summary, we discussed Bayes' theorem and worked out a couple of examples.